Good morning, guys. Today we're going to continue our unit on polynomials by looking at dividing polynomials. Two techniques we've got to work with. Before we get into those, let's just look at division in general. I want you to take this expression here and divide it. These two numbers, 298 divided by 7, but I don't want you to use your calculator. I want you to use long division. Pause the video, take you a couple of seconds, try to divide that out and see if we can kind of rehash the techniques for doing long division by hand. Hopefully you were able to get the answer. Let's kind of go through the setup once again. So to do long division, we have to put it in long division format. A couple of terms real quick. This is the dividend, the one we're dividing into. This is the divisor, the one that we're dividing by. So the divisor goes on the outside, dividend goes on the inside. And then we just go through. 7 can't go into 2, so I go to the next term, or the next digit. 7 can go into 29, so I divide what I can. 7 goes into 29 4 times. So divide by this 29 divided by 7, then we multiply. 4 times 7 is 28. Then we subtract. 29 minus 28 is 1. Bring down our next term, and then bring down our next digit, and we repeat the process. We do 7 goes into 18, or 18 divided by 7, which happens twice. We then multiply that 2 times the 7 by the divisor, gives us 14. We then subtract that, and we would bring down the next digit. Now, at this point, we have no more digits. If you were in 5th grade doing this problem, you would have written R of 4. 7 goes into 298, 42 whole times with a remainder of 4. 6th grade, you learned about these wonderful things called fractions. Maybe before 6th grade, if you were lucky. You learned about these wonderful things called fractions, and it wasn't a remainder of 4. It was 4 out of the 7 pieces that we had left over. So 298 divided by 7 by our long division is 42 with 4 out of 7 left over, or 4/7 remaining. That's long division with numbers. Long division with polynomials is the exact same process. Same process, same steps are going to get us to be able to divide polynomials. So first thing we do is set it up in this long division format, divisor on the outside, dividend on the inside. But be very, very careful and remember to write zeros for any missing terms. And that's because just like here, I was missing a number in the 10 spot, I would have to have a 0 for that number. Okay? We have to have those placeholders. It's the same idea here. If I'm missing an x squared term, I need to put a 0 in the x squared column so I can hold that place value. And that just keeps all of my like stuff lined up, and it cuts out on the miscalculations and confusion later on as you're combining your like terms and doing your subtraction steps. So, set it up in long division format. Remember to put in zeros for any missing terms, and then we go through our steps. Divide the first term of the dividend by the first term of the divisor. So, I like to call that the first divided by first step. First divided by first. That's your first actual mechanical step right there. Second step, when we divide, we're going to get a quotient. We're going to multiply that quotient by the divisor. So, multiply is our second step. Just like we multiplied that 4 back by the 7, after we divided 7 into 29, we are going to multiply whatever we get from our first divided by first back by what we're dividing by. And then your third step, 4 times 7 gave us the 28, and then we subtracted that 29 over 28. So that's your third step. Subtract that product from the dividend. First divided by first, multiply, subtract, and then the next thing is bring down the next. Instead of bring down the next digit, we're going to bring down the next term, and then we repeat. So bring down the next term until the dividend is a lower degree than the divisor. So it should be bring down the next term and repeat until the dividend has a lower degree than the divisor. Same idea. I kept bringing down numbers till I ran out of numbers because the 4 would no longer divide by the 7. Or 4 was too small to divide by the 7. So that's our strategy. You can remember it all like this, or if you'll just remember, set it up and then first divided by first, multiply, subtract, and then repeat that process. First divided by first, multiply, and subtract. Give me a second, I'll get a few examples up here. An example for me to do, and then a couple for you guys to try. Okay, here we have an example that I want to work for you. So going through our steps, first thing, let's get it set up in long division format. What we're dividing by goes on the outside, x squared. Remember, zeros for any missing terms. I have a quadratic term, I have a linear term, so I need to put in a 0. Sorry, quadratic term and a constant. I need to put in a 0 for that linear term. Second, then we put the stuff on the inside. The dividend goes on the inside. So x cubed, 6x squared, minus 5x plus 20. Notice we weren't missing anything here. And you just do a quick rundown of your exponents. 3, 2, 1, none. Here I had 2 and none, so I needed an exponent of 1. Now we just go through our steps. Once we set up, first divided by first. And I like to do just kind of some scratch work off to the side. So x cubed over x squared. First divided by first is x. So I'm going to put it up here. I will usually line up my like terms. It doesn't matter if I put the x right here, 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 here. If I wrote it over here on the board, if I wrote it on that side of the board, if I wrote it on that side of the room, it doesn't matter where I write this x. I just like to line up my like terms just because it kind of keeps it neat and organized, but it really makes no difference where you put it. So, x cubed divided by x squared is x. So first divided by first. Next we multiply. So I'm going to take that x and distribute it to everything over here. All of it gets multiplied by the x. So x times x squared is x cubed. X times 0x is 0x squared. So this is why we need that 0 in for that missing term. That way I have my x squared lined up over my x squared, and x times 5 I get to put over underneath my actual 5x there. So the 0 is just keeping my like terms lined up. It's just acting as a placeholder. So we first divided by first gave us the x. We multiplied to get this expression. Then we subtracted. Now when you subtract, the way I want you to do it, instead of writing minus all this and then having to remember this minus this, this minus this, this minus this, use this little reminder. When you draw your line, I draw my subtraction line, change your signs. So make that negative x cubed, negative 0, negative 5x. So now I'm not having to think of subtracting, I'm now just combining like terms. I've made everything opposite. So instead of subtracting, I'm adding the opposite. So x cubed, negative x cubed should cancel. If those don't cancel, you've messed something up. You need to go back and check the last 2 steps, the last sequence of steps. 6x squared and 0x squared is 6x squared. Negative 5x is negative 10x. And then, okay, we subtract, then we bring down and repeat. So I'm going to bring down that 20. And we start the process over again. Move back to the top. First divided by first. So 6x squared divided by 1x squared. First divided by first gives me 6. Let's put that up top. Then we multiply by that 6. That's step. The next step, multiply by it. So 6x squared, 0x, plus 30. Subtract, so draw my line, change my signs. 6x squareds cancel. Negative 10x and 0x is negative 10x. 20 and negative 30 is negative 10. And now I don't have any more terms to bring down. And I also noticed that if I went back to the beginning of first divided by first, negative 10x over x squared, well, since this exponent is smaller than the bottom exponent, I can't divide that. I would get a negative exponent, correct? I would get x to the negative 2, or x to the negative 1 if I was subtracting my exponents. And polynomials have to have positive exponents. So at that point, I know that since what I'm dividing into is smaller, I'm finished. So I don't have any more terms to bring down, and I have a smaller exponent. If I had a bigger exponent still, I would tag a 0 for whatever the next degree is, and then just pull it down, and we keep going through the process. I'd be putting those zeros on there. But this exponent is smaller than that exponent, so that tells me that I'm finished. So that means this expression down here would represent what? If that's what's left over after I've divided, it should be the remainder. And we should remember, just like we did with the remainder of 4 and we put it over the 7, it's always plus remainder over divisor. Plus the remainder over the divisor. Negative 10x minus 10 over x squared plus 5. Now, I want to show you something as far as cleaning this up. Don't want you to leave it x plus 6 plus negative 10x minus 10 over x squared plus 5. And the reason is we don't want a plus and negative together. So what we do is we know plus and negative is subtraction. So we're going to make this a subtraction symbol. But if that's subtraction, that means the negative doesn't just come off of that 10, it comes off of that 10. It's the entire numerator that's getting changed. So what I have is x plus 6 plus negative 1 times 10x plus 10. All over x squared plus 5. This and this are equivalent statements. I'm factoring a negative 1 out, which I know a negative 1, I could put it on the top, on the bottom, it doesn't matter where it is. So if it's realistically that, the plus a negative makes the whole fraction a minus, and we're left with that expression right there. So if you get that lead coefficient of your remainder to be a negative number, don't do plus the remainder, do minus opposite of the remainder. Minus, and then change the signs on all of the remainder and put it over the divisor. So that's what our final expression should look like. Give me a second, I'll get a couple of examples up here for you guys to try. Here you go, I've got 2 examples up here that I want you to work out. I want you to divide these 2 polynomials and those 2 polynomials. I'll pause the video, take a few minutes, and I will wait right here, guys. All right, hopefully you were able to get the quotient for each of these 2 division problems. Let's check your work to see how you did. First thing we do, set it up. So x squared plus 2x minus 6 is going to go on the outside, divisor on the outside, dividend on the inside. X to the 4th plus 3x cubed minus 5x squared minus 8x plus 6. So we go through, there were no missing terms, 2, 1, none, 4, 3, 2, 1, none. So we didn't have any zeros to plug in. And we've got our 3 steps. First divided by first, multiply and subtract. So I'm going to take my first and divide it by my first. X to the 4th over x squared is x squared, so let's put it up top. And we multiply by that. X squared is x to the 4th, so that checks. X squared and 2x is 2x cubed. X squared and negative 6 is negative x squared. Like terms are all lined up, so everything seems to be okay. Now we subtract, so draw your line, change your signs. X to the 4th, negative x to the 4th cancels. 3x cubed, 2x cubed is 1x cubed. 5x squared and x squared is, negative 5x squared and 6x squared is x squared. Bring down the next term, repeat the process. first divided by first. X cubed over x squared equals x. I'm then going to distribute that. X squared and x is x cubed. X and 2x is 2x squared. X and negative 6 is negative 6x. Now we're going to subtract, so draw your line, change your signs. X cubed negative x cubed cancel. X squared negative 2x squared is negative x squared. Negative 8x and 6x is negative 2x. Bring down the next term. And we know we can keep going because x squared can divide by x squared, so we're still good. And then we repeat the process. First divided by first. Negative x squared over x squared is negative 1. Now distribute that. Negative 1 to x squared is negative x squared. Negative 1 to 2x is negative 2x. Negative 1 to negative 6 is positive 6. And we subtract. Draw your line, change your signs. Negative x squared, positive x squared cancels. Negative 2x, positive 2x cancels. 6 and negative 6 cancels. So we get a remainder of 0 on this one. So like with all remainder 0 problems, we don't have to write anything up there. So that is the quotient of those two polynomials. X squared plus x minus 1. That remainder is very important, having a remainder of 0. We know that whenever you have one expression that divides completely into another expression, then what you're dividing by was a factor of the original. It's a very good concept, important concept to keep in mind as we move forward in this unit and we continue our study of polynomials. Remainder of 0 implies having a factor of the original. All right, let's look at this second example right here. So we're going to set it up. So I'm going to take my x cubed plus x squared plus 0x minus 5. Remember, I don't have a linear term, so I need to have that linear placeholder in there. Divided into 2x to the fourth plus 2x cubed plus 0x squared. There's no quadratic term in this one, so I need that quadratic placeholder. Minus 10x minus 9, and we just go through the steps. First divided by first. 2x to the fourth divided by x cubed equals 2x. Distribute that to every term of the divisor. 2x and x cubed is 2x to the fourth. 2x and x squared is 2x cubed. 2x and 0x is 0x squared. 2x and negative 5 is negative 10x. Now we'll subtract. Draw your line, change your signs. 2x to the fourth, negative 2x fourth cancels. 2x cubed, negative 2x cubed cancels. 0x squared, negative 0x squared cancels. Negative 10x, positive 10x cancels. Bring down our next term, negative 9, and we repeat the process again. Only problem is, negative 9 is a constant. That's a cubic. Well, x to the 0 is smaller than x to the third, so negative 9 is our remainder. So our answer ends up being 2x plus the remainder over the divisor. X cubed plus x squared minus 5. And remember, I don't want plus a negative, so I'm just going to make that negative out front, and the numerator now becomes positive. So that is the quotient of this polynomial divided by that polynomial. So even when they look big and nasty, may not have many steps to it, as that one did right there. There's another technique that we're going to look at for doing for dividing polynomials. Works for a little bit simpler polynomials. Long division works in any case. So you need to know this and be comfortable working with it. But I'm going to show you another technique called synthetic division that works in special cases, and it's a little bit faster. Some people like it, some people don't, but long division will work for all of them. Give me a second and I'll get the synthetic division stuff up here. So let's talk about synthetic division. As I said before, long division works no matter what you're dividing by. Synthetic division will only work if you're dividing by a linear binomial that has a lead coefficient of 1 and k is an integer, or your constant is an integer. So x plus 3, x minus 5, x plus 100, x minus 67. It's got to be 1x to the first degree plus or minus some whole number. So there aren't a lot of cases where we can use it just in the grand scheme of math compared to all the things that you could do that you can't do with it. But it does have a lot of value, synthetic division does, for what we're going to be doing as far as working with linear factorization. So this is something you want to be familiar with because it is a little bit quicker than your long division. First thing we're going to do, we're going to set it up in long synthetic division format, and we're going to remember to put zeros for missing terms. So here's how synthetic division works. We always want to work off opposite of our constant, opposite of what we're dividing by. So if this is an x plus 1, I need to be working off of the opposite of that, and that's going to be minus 1. And I'm going to set up this table. It's going to be 2 rows wide, or 2 rows tall. Now, I'm just going to put the coefficients in. I'm not going to put the variables in. The location of each coefficient is what tells me what variable it's associated with. So I like to label ahead of time that this is going to be my x cubed column, this is going to be my x squared, this is going to be my x column, this is going to be my constant column. You know what? I should pick a different. We'll just go with C right here. It doesn't matter what it is. I just like to have that be K for my constant. So we'll just let that be C, and then we'll work off of the opposite of C. Okay. So if that's positive, that's negative. If that's negative, that's positive. All right, so we want to work off the opposite of that number. So that's -1. Got my columns labeled. Now, I even like to label what my answer is going to look like. And it's going to be this third row down here. Now, this third row works this way. My last column, I'm going to put a box around it. Here's why. I'm taking x cubed and dividing it by x. So we know that should give me an x squared. And I'm taking x squared and dividing by x. That should give me an x. And x divided by x, that should give me a constant. And my constant divided by x can't be done, so that should give me my remainder. So when you set up like this, we're only going to work with the numbers, but the variables are implied based on their position. So this was x cubed, x squared, x constant. So all of these have to be 1 less. And it's always going to be 1 less because we can only divide by an exponent of 1. So you're always going to be decreasing your original degree by 1. So if this had been like x to the 10th, I'd have gone 10th, 9th, 8th, 7th, 6th, 5, 4, 3, 2, 1. And then this would have been 1 less. X to the 10th here, that would have been x to the 9th for my quotient. So 9th, 8th, 7th, 6th, and all the way down to my remainder. So that's the setup for it. Now we're going to plug in our coefficients. So the coefficient of x cubed is 3. Coefficient of x squared is -4. Coefficient of x is 2, and my constant is -1. And the other reason I like labeling this, if I'm missing something, say I didn't have that x squared, well, in my x squared column, that would remind me to put a 0, because there's 0 x squareds in there. So you still have to put in zeros for any of the missing terms to act as placeholders. So once we're set up, it goes really fast. Setup's usually the longest part. Add the columns, multiply that sum. That's it. Add the columns, multiply the sums. So when I add my columns up, 3 plus nothing is 3. And then I'm going to multiply that by the opposite of C. This C, this constant, was a +1, so I'm going to be multiplying by a -1. So -1 times 3 is going to give me -3. And we just put that in the next column. Then we add our column up. -4, -3 is -7. Add the column, multiply by the opposite of C. So -1 times -7 is +7. Add the column. 2 plus 7 is 9. Multiply by the opposite of C. Negative 1 and 9 is negative 9. Add the column. Negative 1, negative 9 is negative 10. And then we're finished. We have no more numbers, no more columns, so we know that that's it. So here's your answer. 3x squared minus 7x plus 9 with a remainder over our divisor. And like before, I don't like plus and negative remainder, so we'll make that negative 10 over x plus 1. So that's how you will do synthetic division. Get it set up, and then it's add the column, multiply by the front. Add the column, multiply by the front. Add the column, multiply by the front. You just keep repeating that process again and again and again until you get till you run out of columns. Give me a second, and I'll get a couple examples up here for you guys to work. So you can see here I've got a couple of examples up for you guys to work. Do each of these, find each of these quotients using synthetic division, and I will wait right here. Pause the video. Okay, hopefully you were able to find each of these quotients. Let's go through and check your work. So I'm going to start by working with the opposite of my constant there. So I'm going to use negative 2. I've got x cubed, x squared, x, and a constant. For the denominator, or sorry, for the answer, I'll have x squared, x, constant, and remainder. Plug in our coefficients. X cubed is 1. X squared is negative 2, x is negative 5, my constant is 6. And then we just go through and do our 2 steps. Add the columns, get 1, multiply by the front, get negative 2. Negative 2 times 1 is negative 2. Add my column, get 0, multiply by the front, negative 2 times 0 is 0. Add my column, get negative 5, multiply by the front, negative 2, negative 5 is 10. Add the column, get 16. We're out of column, so we're finished. So this is going to be our quotient. 1x squared with no x's minus 5, right? 1x squared plus 0x minus 5 plus remainder over divisor. Let's look at the next one. Let's set it up. You start with the opposite of your constant. So there's 4. Now, x to the 4th is our first degree. So x cubed, x squared, x constant. For the quotient, that's got to be 1 less. X cubed, x squared, x constant, and there's my remainder. Plug in our coefficients. X to the 4th was 2. X cubed was negative 3. There wasn't an x squared, so I need to put the 0 there, have that placeholder. X is 4. Constant is negative 6. And we go through and do the steps. Add the columns. 2 plus nothing is 2. Multiply by the front. 4 times 2 is 8. Add the column. Negative 3 and 8 is 5. Multiply by the front gives me 20. Add the column. 0 and 20 is 20. Times the front is going to give me 80. Add the column. I get 84. Times the front is 320, 336. And you add that last column up and you get 330. Okay, now, assuming my arithmetic is correct, I'm going to show you in a second how we can check and make sure all of that arithmetic is correct. But we should have 2x cubed plus 5x squared plus 20x plus our constant, which is 84, with a remainder of 330 over what we divided by, x minus 4. Now there is a concept called the remainder theorem. Remainder theorem says that a polynomial evaluated, let's try this again. A polynomial evaluated at some number, we'll call it C. Okay, so we're using C for it. A polynomial evaluated at C is the same thing, is equal to the remainder of that polynomial divided by x minus c. So here's what remainder theorem actually tells us. If I divide a polynomial by a linear binomial, that remainder that I get from that is the same thing as if I had taken opposite of that constant and just plugged it into my function. So what we see right here, I said 330, assuming all my arithmetic is correct. Well, let's check and see if my arithmetic is correct. Let's take this function, 2x to the fourth minus 3x cubed plus 4x minus 6, and instead of dividing it by x minus 4, let's evaluate it at the opposite of negative 4. We'll evaluate at that 4 that we divided by. So if I do 2 times 4 to the fourth minus 3 times 4 to the third plus 4 times 4 minus 6, as we go through, we just do our arithmetic. 4 to the fourth is what? 4 squared 16, 16 squared is 256. Minus 3 times 4 cubed, which is 64. 4 and 4 is 16 minus 6. 2 and 256 is 512. 3 and 64 is 180, 192. 16 minus 6 is 10. I'm going to start cleaning that up a little bit. So 512 minus 192 is 412, 410, 320. 320 plus 10 equals 330. So by the remainder theorem, plugging in a 4 into my function gave me the same thing that using a 4 to divide my function as the remainder. It seems like a very trivial thing, but what that tells us is something that we're going to look at coming up, is being able to test and see that I get a remainder of 0. So if I want to be able to evaluate and get a remainder of 0, that'd be the same thing as plugging in to get 0. Or if I was to divide and have a remainder of 0, that'd have been the same thing as plugging in and getting the 0. So the remainder theorem is a useful thing for what we've got coming up as far as trying to identify zeros in a quick manner. And it's also pretty easy, I would say. An easy way to evaluate a function. Say I had something like x to the 7th, x to the 8th, x to the 9th, some very large degrees, and you're evaluating without a calculator. Well, I don't want to have to do like 16 to the 7th degree. But if I could do a synthetic division with a 16 and then build in a lot of small multiplications and additions, then I could get the evaluation in that manner also. So remainder theorem has some uses to it outside of just being a trivial little check to make sure that we've done our synthetic division correctly. So make sure you're familiar with it because we will use it in a couple of different manners in class. That's dividing polynomials, long division, synthetic division. Long works always, synthetic works if we're dividing by a linear binomial with the constant of as an integer. It actually can work if our lead coefficient, still have to be linear, but if our lead coefficient is not one we can make it work, but there's a lot of tweaks that have to be done to our function for that to happen. So we're gonna, or to our quotient for that to actually give us the correct answer. So we're gonna focus on just lead coefficient of 1 in our linear binomials when we're doing synthetic division. That's dividing polynomials, and I will see you in class tomorrow, guys.